Well, good morning. This is Tuesday morning, 9:32 in the morning, the 14th of March, 2017. Time for pre-calculus algebra, math 113. Pre-calculus trig, math 113, but I'm the only person in the room, so I don't know where my 10 students are. I hope you're coming soon, okay? But today we're starting. I would be asking if there are any questions. Nobody's here to ask, so it doesn't make any sense to. We are starting chapter 5, which is analytic trigonometry, okay? And in this, there's 5 sections, so we'll have a test at the end of section 5. And 5.1 starts with using fundamental identities, okay? Now, if you think back, we have talked about these identities, and just want a quick refresh, okay? Okay. In chapter 4, we started talking about basically radian and degree measurements, so we didn't have any identities there. But once we got in 4.2, we had your started off, well, no, didn't actually do any identities there. We laid the groundwork for them. We gave the definitions of them a couple of different ways, okay? 4.3, more of the same, and we started in on page 282, chapter 4, section 4.3, fundamental trig identities, okay? Later, in 4.4, we had the definition of trig functions again for the third time, and though we used the identities, it didn't list them again, but we were always using them. And then in 4.5, again, we used them but didn't list them again. In 4.6, when we did the graphs, again, we used them but didn't list them. Okay. 4.7, again, we used them but didn't particularly list them. And 4.8, we used them big time. Big time. I don't believe we listed them again. Okay? But the definitions we gave at least 3 times, and the identities in one table once. It seems like there's more than once, I just didn't see them. I'm sure at the chapter summaries they were listed again. I forgot to check those. But now in analytic trigonometry, here we see them again. Okay? Using the fundamental identities. Our objectives here to recognize and write the fundamental trigonometric identities. And then number 2, use the fundamental trig identities to evaluate trigonometric functions, simplify trigonometric expressions, and rewrite trigonometric expressions. Okay? So the introduction, we will learn to use the following fundamental identities to do each of the following, as if we have to state them again. Evaluate trigonometric functions, simplify trigonometric expressions, develop additional trigonometric identities, that's a new one, and solve trigonometric equations. The order is a little bit different, but they're the same listing as before with one added. And here they are again, the fundamental trigonometric identities. Your reciprocal identities, which, if my memory was right from the last class, a few of you were a little even slow on these because you weren't remembering to use these, but the sine is 1 over cosecant, cosine is 1 over secant, tangent is 1 over cotangent, cotangent is 1 over tangent, secant is 1 over cosine, and cosecant is 1 over sine. And I like to list them, sine, cosine, tangent, cotangent, secant, cotangent, a lot this way. Usually I do them more vertically, these is horizontally, but you see you're pairing up your reciprocals, sine and cosecant, cosine and secant, and tangent and cotangent. Okay? Your quotient identities. I've also heard these referred to, and I like to call them ratio identities. Tangent is the ratio of sine to cosine, which then, because cotangent is reciprocal of tangent, it would be the ratio of cosine to sine. And then your Pythagorean identities, okay? And it lists 3 versions of it here. You can do several versions. The primary one is sine squared u plus cosine squared u is equal to 1. Always, always, always true. That's what makes it an identity. It's not a conditional equation. This is true for any value you put in there. The second one, if you divided that first identity by sine squared, no, by cosine squared, let me get my pen activated here. I think I did this for you before. Divide this by cosine squared theta, or cosine squared u. Divide this by cosine squared u. And divide that by cosine squared u. Well, what do you get? Sine over cosine from your quotient identity is tangent. So that would be tangent squared u. Cosine squared over cosine squared is 1. So 1 plus tangent squared u is equal to 1 over cosine squared u. What is 1 over cosine squared u? Secant squared u. So 1 plus tangent squared u is secant squared u. Now, and by the way, let's go back to the first one. Sine squared plus cosine squared equal 1. You could subtract the cosine squared from both sides. That would give you sine squared is equal to 1 minus cosine squared. You could subtract sine squared from both sides. That would give you cosine squared is equal to 1 minus sine squared. You could take a square root of either one of those and have the square root of 1 minus cosine squared for sine, square root of 1 minus sine squared for cosine. There's a lot of different ways you can put those together. Same thing with the second one here. You can subtract 1 from both sides and have tangent squared is secant squared minus 1. You could subtract tangent squared from both sides. You could have 1 is equal to secant squared minus tangent squared. And then you could take square roots as well. Usually we don't, but we could. On the third one, and how you get that third one is then dividing not by cosine squared, but by sine squared. And sine squared over sine squared would be 1. Cosine squared over sine squared would be cotangent squared. And 1 over sine squared would be cosecant squared. Okay? So, and then you could rearrange that in several ways. Cotangent squared is equal to cosecant squared minus 1. 1 is equal to cosecant squared minus cotangent squared. And then you can take square roots that we usually don't. Now, the cofunction identities we talked about a little bit. I usually don't think of them in this form necessarily, though this is certainly true. I just remember that and it's saying the same thing this says, the sine of the complement of an angle is the cosine of that angle. Okay? The cosine of the complement of an angle is the sine of the angle. The tangent of the complement of an angle is the cotangent of that angle. The cotangent of the complement of an angle is the tangent of that angle. The secant, thank you for being here.
Tyler's here too. He's in the bathroom. Tyler's here too.
Is it? Okay. Goodness, I thought if I'm going to talk to myself all the term, I'm going to be nuts by the end of the class. All right.
You just wouldn't have anybody to answer anything.
Right. Well, while y'all are coming, I'll go and turn on the projector. I'm going to say it on the book. Somebody's here to see it. And I'll flip the lights. Okay, Johnny comes lately, huh?
How does it feel like teaching? Oh, I don't know. I'm sorry. I'm moving it. I'm sorry.
She's in your seat. Oh my goodness. These are Baptists, right? Huh?
Sorry.
You better not sit in my pew. Right. Yeah.
He's going to end up beating me up. It just feels so far back. I don't like it.
There's a guy in our church. He has to sit in the same spot all the time. He gets mad. He'll throw a fit if he don't get to sit.
Oh, that's I've even heard it at our church on Wednesday night suppers. You better not bid in somebody's place, and it's not real obvious what their place is. Yeah, so what the staff does sometimes change it from long tables to round tables. It really confuses me.
They do it on purpose.
Huh?
They do it on purpose.
I have known them to do it on purpose. It wasn't the staff; it was actually a committee member, a session member, said, "Let's just change tables." What? I didn't see one, and no one else has been in here, so yes, not. Amber may have stolen it. She's real bad about that. She's a
I
tough
know I'm
lady.
bad about taking people's seats, taking people's pens.
Yeah.
I get no credit for anything.
Might be able to spray for a pen if you need it. Huh? Yeah, I lose them all though. I sure haven't seen it. All right. I had already started. There weren't any major announcements I knew of today. The only thing I didn't put it on because it wasn't that big a deal. Did you ever find it? Still not? Okay. I believe on Thursday we have a faculty meeting. But the good news is it doesn't interfere with the classes in the afternoon. Hey, I can tell I made your day. Okay. Still not? You need a pen? Okay.
Where are we at the book?
This is on page 350, section 5.1, chapter 5.
So we're in chapter 5.
Yeah.
Where are we going to get the next test?
I thought I gave it to you.
You left early.
Oh, that's right. I was thinking you were here. I'm not deep enough, I don't think. Okay.
I need you to calm down.
Okay.
I have PPE right after this, and I have to be able to get ready for
Said
PPE.
you eat. Right.
Physical education.
You have that for college.
Yes, you have to take it in or if it's on your curriculum. I have to take two. I have to take 2 hours of it.
I ain't heard that before.
Well, your
You haven't
curriculum.
looked at your grade plan, have you?
I haven't looked at my degree.
Obviously.
It's under area 5 and it's kind of buried there. But
Yeah, it says PE, and it's,
Yeah, I did.
you can choose what you want to do. I chose gymnastics, and then I might do like yoga or something.
They also have personal fitness, weight training,
Nutrition.
exercise.
Dance
Is there a
aerobics.
legal class?
Yeah, I don't know.
It
They're
weird.
jogging. Huh?
It weird.
What?
Yeah, I feel very like all we've done so far is walk around outside.
Really?
That's what we did last week because like this is his second midterm course,
Right.
and so the first class he went over like everything we're supposed to do, everything else. You show up, you get 20 points, pretty much. You show up all night,
Right.
and you have to dress appropriately and just trot, pretty much. And what we did last time was walk and then check your heart rate and then left.
When did you just stay there?
Most be easy movements.
And who you got?
It's the baseball coach.
Oh, okay.
Do you have to do it?
He's
Do you do the
alright.
right names?
Huh?
I'm just saying.
Do you have to do the right names?
No, it's him.
I didn't know the baseball coach was here. I thought he was always at Birmingham games. That's where the field is.
Well, he's teacher.
He's also a PE teacher. Everybody's required.
He's also here Mondays and Wednesdays.
Oh, really? Okay.
I think he said he has one or 2 classes on Mondays and Wednesdays. This is the only class on Tuesday.
Okay. So he's here all day, Monday and Wednesday? Or just sometime?
I think
That's
it's
so strange. It seems like they Give
And
them
then he
either
said-
Monday, Wednesday, or Tuesday, Thursday on one campus, and I have them going back and forth.
And he said Thursdays he might not always be here because of baseball.
Yeah.
Which I don't mind. So.
Yeah, I know I have a baseball player in my class right before this, MTH113, and I know some days he's out because of games. Okay, and on your test, by the way, the first 9 are graphing. That's why I gave you graph paper. So if you can squeeze, 5 and 4 on those graphs, that would be fine. If you need more graph paper, I didn't ask you, did you need graph paper?
I think I have some at home, but
If you don't want to use that because it's sort of cruddy, you can give it back to me. I'll give it to some of my cruddy seats.
so it's 1 through 9.
1 through 9 is graphing, yeah. And then the rest of it is,
I see.
okay. All right. Okay. And so that is here. All right. Bottom part of the alphabet's doing fairly well. Top part missing completely. Okay. Okay. I was talking about these before anyone came in, because I was talking to myself. I was down through the co-function identities, so you can listen to the YouTube to get what you missed so far. But the co-function identities, I'll go over. I already said something. The sign of the complement of a function is the same as the cosine of that function. The cosine of the complement of a function is the same as the sine of the function. That's what the code means, by the way. Complement. Tangent of the complement of an angle is the cotangent of that angle. The cotangent of the complement of an angle is the tangent of that angle. The secant of the complement of an angle is the cosecant of that angle, and the cosecant of the complement of an angle is the secant of that angle. Okay. And then the even and odd identities. Sometimes I just don't even think of these as identities, but they sort of are. Because sine is an odd, and here's the other thing. Your trig functions, remember in regular functions, occasionally you'll have a function that is either even or odd, but most of them are neither, okay? In trig functions, most of the time, in fact, the basic functions are all either even or odd. They're not neither. The sine is an odd function, which means that sine of minus u is minus sine of u. That makes cosecant an odd function because it's reciprocal of sine. Your reciprocal identity. So cosecant of minus u is minus cosecant of u. However, cosine of minus u is the same as cosine u. That's because it's an even function. And the secant, because it's reciprocal of cosine, it is also an even function. The secant of minus u is the same as the secant of u. Now, tangent of u is sine over cosine. Odd over even, the odd holds out. So it's an odd function. So tangent of negative u is negative tangent u. And because it's reciprocal of that, the cotangent of negative u is the negative cotangent of u. So 4 of the functions are odds, only the 2, the sine and the cosine and the secant are even. Make sense? We will use and call upon these identities repeatedly, over and over and over. I want to say constantly. You'll never get enough of these. They're always being used. Maybe not in the same orders and stuff, but they always. And especially in this chapter. Okay? So, how do we use these? Now, the Pythagorean identities, and if you were here, you weren't, but when you listen to the YouTube video, you'll hear me say this. You can sometimes rewrite those and take square roots on them. So sine of u, remember, sine squared plus cosine squared is equal to 1. Pythagorean identity. Subtract cosine squared from both sides. You have sine squared is equal to 1 minus cosine squared. Then you can take the square root of sine squared. You get sine of u, but that's going to be either plus or minus the square root of 1 minus cosine squared, depending on where the function is. If it's in the first or second quadrant, you're going to use the plus sign. If it's in the second a third or fourth quadrant, you use the minus sign. Because sine is positive, first and second, negative second, then third and fourth. Or you can do the same with tangents. Remember though, 1 plus tangent squared is secant squared. So you subtract the 1 from both sides and you get tangent squared is equal to secant squared minus 1. Then take the square root, and then tangent u would be plus or minus the square root of secant squared u. How you determine which sign to use? Where are you, Waldo? Where is u? If u is in the first or the third quadrant, then use the plus sign. Second or fourth quadrant, use the minus sign. So the sign depends on what the value of u. Usually you don't choose u, you're given u, So anyway. Hey. And Landria's here. Okay. 4 out of 10. So we still got 6 missing. But I'm glad y'all are here.
You said
Yes.
U was in the first or the third?
For tangent? Yeah. First or third quadrant, tangent is positive. And the second and fourth quadrants, tangent is negative. Remember our little acrostic? All students take calculus. All the trig functions are positive in the first quadrant. Only sine and its reciprocal, that's students, sine and reciprocal, which is cosecant, positive in the second quadrant. Take tangent and its reciprocal, cotangent, positive in the third quadrant. And calculus, which is cosine, several start with C, cosine and its reciprocal, secant, positive in the fourth quadrant. All right. Now, using the fundamental identities, okay? One common application of trigonometric identities is to use the values, given value of trigonometric functions to evaluate other trigonometric functions. And that's what we do in example 1. Use the values of secant u. If you're told, you're given, the secant u is equal to negative 3/2. Okay? James is here. Okay. Did you get the second test? Okay. Landry, you got the second test, didn't you? Okay. Did I go deep enough? Nope. Too deep now. Okay. All right. Do you need graph paper? Okay. And let's see. Here's test 2. Now there's 9 to graph, so if you can get 5 on one page and 4 on the other, it's fine. If you need more graph paper, I can get it. I had asked the secretary to do it duplex, and she only did it simplex, so I've run out, but I've got more. Okay. So it says use the values of secant u, which is negative 3/2, and the fact that tangent is positive. Tangent of u is positive, greater than 0, to find the values of all 6 trigonometric functions. Now, there's several ways you can go on this. I know how they want you to go, but I'll show you what I think is just as easier way to do it. But I want to get your opinion. First, they've given you what secant u is, negative 3/2. What does that tell you about u? Just the fact that secant is negative 3/2. What can you conclude about the angle u just from that? Tells you something. The fact that secant u is equal to negative 3/2. As in, where are you, Waldo? Say again? Okay, the fact that the secant is negative, what does that tell you about where you are? Which quadrant? Yeah. That narrows it down to 2. Which quadrant must you be in if secant is negative? Second? Okay. The first quadrant, all trig functions are positive, so it can't ever be the first. Okay? Ever. Not for it to be negative. Okay? Third, yeah, secant is negative in the third quadrant. But that's not the only quadrant where it's negative. Fourth quadrant, no, secant is positive fourth, because secant is reciprocal of cosine. Okay, she got it on the third try. Okay. So that means that the fact that secant u is negative 3/2, that means you're either in the second or the third quadrant. Now, it also tells you that tangent u is positive. Now, this may have been what Chevette was answering. What does that tell you? If tangent is positive, that tells you you're either where? First or third. Okay? So if secant u being negative tells you got to be either in the second or third quadrant, and tangent being positive tells you you're either in first or third, guess where you are, Waldo? Third, because both of those fit. Okay, so you're in the third quadrant, and it says to find the values of all 6 trigonometric functions. Now, I know how they want you to do this, okay? However, I'm going to show you the way that I think is a little better, okay? Draw a picture. You should have seen that coming, couldn't you? You know you're in the third quadrant down here. Now, can anyone tell me what secant u is equal to? And I like to use x, y, and r. But you can use adjacent, opposite, and hypotenuse if you want to. But x, y, and r, they fit the bill too. What is secant u equal to? Secant u is always what? Secant u is always, okay, tell me its reciprocal identity, if that would help any. Secant u is? Say again? Say again, you may have been right, I just can't hear well. Did you say x over r? Okay. X over r, x would be the adjacent side and r would be your hypotenuse. The adjacent side is always less than the hypotenuse. Does that look like that can be it? Because 3 is not less than 2. Huh? Other way around. It's the hypotenuse over x, or the radius r over x. Okay? So, okay, now. So secant u is r over x. Okay, we have a minus sign there, obviously, right? Now, tell me this. Which of those could be negative, r or x? Either, both? R is never negative. Remember, it's your radius. The square root of x squared plus y squared. Never negative. Hypotenuse is never negative. So that means say again? Yeah, x can be negative, can it? Here's -1, -2, -3. +1, +2, +3. +1, +2, +3. +1, +2, +3. X equal -2, R equal 3. So basically what we do is complete the circle. Ew, that's an ugly circle. Who drew that? Okay. Here is your angle right there. Here is your angle U. With X being -2, R equal 3. Okay? And we know since it's in the third quadrant, your tangent is positive. That fits. So can you give the values of all 6 trigonometric functions? What are the 6 trigonometric functions? Sine, u, cosine, u, tangent, u, cotangent, u, say again? I can't hear you. Secant u and cosecant u. Okay? Now, all we know so far is secant u is minus 3/2. Okay? What's the easiest one of the other 5 to do? Very easiest. And use your identities. Second, cosine, of course. What would it be? Negative 2/3. Because the cosine is reciprocal of secant. There's your reciprocal identity right there. All right. Now, what's another trig function that's related to secant? We know cosine is its reciprocal. What's another one that's related by one of our identities? A little louder. Okay. Sine is not at all related to secant. It is a little bit to cosine. Say again? I can't hear. Tangent. How is tangent related to secant? Okay, I can't hear. Okay. Okay. You're doing, I think, a good thing there. Okay. By the way, the cosine was x over r, and we got that, negative 2/3, got it. And what did you say sine was? Or which tangent? I don't care. Oh, tangent, you said. What was tangent? Y over x. All right, very good. We've got the x and we got the r, but we don't have the y. So are we completely out of luck here? What you think? Why not? Of course we can. Pythagorean theorem tells us what? That your y is equal to a little louder. Okay, that's your Pythagorean theorem. Which are you calling A? Second? I can see you're writing in the air, but I can't read it. Okay. Negative 2 could be your A, okay. Why don't we just call it X, okay. And what would you call in your B? The what? No. Your R is always your hypotenuse. Jasmine's here. Okay. So the hypotenuse is your R. That's your C, and that's your 3, okay, and that's your hypotenuse, okay? So that would make your b, or your other leg, to be the y. So your Pythagorean theorem, according to what we're using, x, y, and r, would be x squared plus y squared is equal to r squared. Right? That's true too, right? Now, we know x, that's a negative 2 squared, plus y squared, we don't know, so leave that alone, is equal to r squared, but r is 3, so this would be 3 squared. Solve that for y. First, what's negative 2 squared? 4 plus y squared is equal to 9. What would be y squared be? A little louder. 5. So what would y be? Second? Almost. Second? Plus or minus, but which is it? Second? Minus, you're in the third quadrant. So your y is equal to negative root 5. Okay, very good. I feel like a dentist. Okay? Now that we have this, you can write them all down, can't we? We could start with tangent if you wanted to, but you could do any of them because we have all 3 of our legs of the triangle. So what would your tangent be? Root 5 over 3. Very good. And that would be positive because tangent is positive in the third quadrant. It's minus divided by minus. Okay? Sure enough, that's possible. Say again? Oh, 2. I'm sorry. I wrote the wrong number down. Can't get my pen to activate. Here we go. Well, it's moving really slowly. I'm sorry, it's a 2. Root 5 over 2. And now that we got that, what could we do really easily? Cotangent. What would cotangent be then? 2 over root 5. Now, if you don't like having a radical in the denominator, how could you write that? 2 root 5 over 5. Okay, that would be fine too. I don't care. Okay, can you do either sine or cosecant now? Sine, what would sine be? Root 5 over, or negative root 5 over 3. Because remember, the root 5 is negative. You didn't need that for tangent and cotangent because the 2 was negative 2, so those came out positive. So that would be negative root 5 over 3, and what would be your cosecant then? Negative either 3 over root 5 or negative 3 root 5 over 5. All right. Good deal. Now, that's how we did it. That, to me, is the easiest way to do this. If they give you one of these, any one of these, that gives you 2 of your measurements. Figure out where you are, Waldo, okay? And draw the angle, draw the sides, and then identify 2 of the 3. You can always calculate the third one with the Pythagorean theorem and knowing where you are. Now, that's probably not how they wanted you to do the problem. This part, yeah, for sure. This to that was a just reciprocal identity. 1 over this one is that. That was easy. And that using your identity. What they wanted you to do next was the Pythagorean identity, just like we used the Pythagorean theorem here to get that other side. What they wanted was tangent squared is equal to secant squared minus 1. So you could have squared this. That would be 9 over 4. Subtract 4 over 4 from it, and that gives you 5 over 4 and then take a square root of that, that would be root 5 over 2. Okay? Done. Okay? And then you could use your ratio identity. Your reciprocal identity, that then told you this was 2 over root 5, which is also 2 root 5 over 2. That tangent was real easy. And then you could use your ratio identity that this was equal to sine over cosine. Well, the cosine has a 2 in it, a minus 2. So that's down here. So this must be a minus 5 over the same arm. 3. Okay? And then once you have sine and reciprocal identity, you get cosecant. Either written like this or like that. All right. Now, I know they wanted to use those identities. And we did use some. But rather than Pythagorean identity, I just used the Pythagorean theorem of the sides. And you got the same result. So let's see how they did it. If I could get the eraser to come up. The system has gotten awfully slow all of a sudden. Okay. So how do they begin? They first locate where you are. No, they don't. They just jump right into it. Using the reciprocal identity that cosine is 1 over secant, knowing secant is negative 3/2, cosine will then be negative 2/3. Okay. Got it. That's the easy one. Okay, the next one, they're going to use the Pythagorean identity. And they use sines and cosines. Sine squared is equal to 1 minus cosine squared. We already knew cosine squared. Okay, we knew cosine. So we knew cosine squared. That would be 4/9. So this would be 1 minus 4/9 is 5/9. Okay, so that means sine would have to be square root of 5 over 3. But plus or minus, that's what we don't know yet. Or we knew, but they didn't handle it yet. 1 minus a negative 2/3 squared, which would be what? 5/9. That's sine squared. And because secant is negative, but tangent positive, you have to be in quadrant 3. In quadrant 3, the y value, which is the 5, y value is root 5, would have to be negative. Moreover, because sine is negative when u is in quadrant 3, we choose the negative root and obtain sine u is equal to negative root 5 over 3. I'm sorry. Yeah. First identify which quadrant you're in, then since sine is negative in the third quadrant, this is sine squared, take the negative square root, that'd be negative root 5 over 3. Okay. Now, once you have sine, reciprocal of that is the cosecant. Knowing the value of sine and cosine enable you to find the values of all 6 trigonometric functions. The cosecant is negative 3 root 5 over 5, or negative 3 over root 5. The cosine we already had determined was negative 2/3, and they gave us it. I can't believe they did this. I cannot believe they did this. Do you see anything wrong with that picture? Yeah, but they put it in the wrong place. This should have been here. And that's the right answer for that. But this is the wrong answer because this isn't. This should be down here. They flipped these two. Totally wrong. How could they miss that? Okay? Whoever the graphics guy was, they really messed up. Okay? These two switch places. Okay? You know what gave it away to me? If you remember the original problem says secant u is equal to negative 3/2. you didn't have to calculate it, they gave it to you. And they gave it wrong here, they have up here. So totally wacko. They did that reciprocal here, this reciprocal there. They converted this to that properly, but put it in the wrong place. It's crazy, okay? In the book, they've got it right, okay? Now, they didn't use the Pythagorean identity the way I thought they were. They used Pythagorean identity here, which is perfectly fine. Then once they have this, tangent then is sine over cosine. Just put one over the other. The 3's go out, and you have positive root 5 over 2. And that's exactly what we got. Okay? And then they do the cotangent is reciprocal of that. That would be 2 over root 5, which would be 2 root 5 over 5. Okay. Sorry about a really major bad slide there. Okay. Can't believe the one that they gave you, secant u was equal to negative 3 halves. They didn't even have to calculate anything. Just write it down. They gave it to you. And they got it wrong. Okay. Duh. All right. Example 2. Let's simplify this expression. The other one was using identity to evaluate a function. That's what we just did. Now we're going to use identities to simplify a function. Well, do you have to use only identities? No, use all the techniques you have at your disposal. So what would be the first thing that would come to mind if you were told to simplify that expression? The first step of simplification. Factor! What can you factor here? Factor out a sine. And what does that leave you with? Cosine squared x minus what? 1. Okay. Now, that cosine squared x minus 1, that kind of looks a little familiar, but not quite right. What does that look similar to? Say again? See you drawing, I hear you say something, but I can't make out what you're saying. My hearing's too bad. What is it? Cosine squared x minus 1. Here's a hint, folks. Here we go. Here's your identities. Where do you see squares? Always your Pythagorean identities. So if you have a problem that has squares in it, think Pythagorean. Okay. Now, I don't think anyone was in the room when I said this, because I started talking to myself. You can rearrange this one how? Sine squared plus cosine squared equal 1. Several ways you can rearrange it. What's one way? Subtracting cosine squared from both sides, what does that give you? Sine squared is equal to? Subtract it from both sides. Let me erase what's on here. Okay. What we're going to do is subtract cosine squared from both sides. And that would give you, that goes away, that would give you sine squared u is equal to 1 minus cosine squared u. Okay? That's what I'm getting at. That looks very similar to what we had, except what? Yeah, we have cosine squared minus 1. So how do you make that change? Say again? Multiply by -1, exactly. So therefore, if you multiply this side by -1, you get cosine squared u minus 1, and multiply this side by -1, you get minus sine squared u. There's your new identity, okay? Cosine squared minus 1 is equal to minus sine squared. So let's go back here to where we were. Here. So what does this? This goes to this, and what does this go to? Sine x is still just sine x. But what do we just determine that cosine squared x minus 1 is? Negative sine squared x, right? And when you multiply those two together, what do you get? Negative sine cubed x. Done. There, you simplified that down to here. I'd say this is a lot simpler than that, wouldn't you? All right, good deal. Want to watch them do it? Of course you do. Everybody got it? Okay. Then what do they do? First, factor out the common monomial factor, which is sine x, which is exactly what you did. Now, at this point, that looks familiar. Not quite a Pythagorean identity, but really close. You think of that because there's a square there, but 1 minus cosine squared is sine. So if that's the case, then cosine squared minus 1 must be, okay, what they did, they factored out a minus 1 to get this in the form they needed, and they moved the minus 1 in front. Okay? So they moved it that way. We did it slightly differently. And this is minus sine times sine squared then, because 1 minus cosine squared is sine squared. That's your Pythagorean identity. And then this multiplies with negative sine cubed x, which is exactly what we got. So sure enough, this simplifies to do that. Any questions? All right. Reminder, you have checkpoints after every example. If you found these a little challenging or something, by all means, either when you get home, when you get to another classroom, library, somewhere like this, as soon as you can, try to do some of the checkpoints. Okay. Look at that. They jump from example 2 to example 7. So let's back up and do example 3. All right. And by the way, folks, I left my watch somewhere this weekend. I've got to go back and get it. So I don't have my, I meant to bring up my cell phone, but I forgot to bring it up. So I don't have time. So y'all let me know. I know we got plenty of time. But y'all just keep. I sort of had a feeling you might. Y'all are very kind that way. Okay. Very kind. Okay. It says factoring trig expressions. It says to factor this. Secant squared theta minus 1. Factor that. How could you do it? Yes, secant theta plus 1 times secant theta minus 1. Very good. Okay? Not much else you can do to it. Okay. Except, when I see this, you know what I think? See the square? Pythagorean identity. Right? And secant squared minus 1 is tangent squared. So believe it or not, this product here is tangent squared. To me, it would have been simpler just change that to tangent squared. They did it this way, which is fine. They said factor it, we factored it. How about the B one? 4 times tangent squared theta plus tangent theta minus 3. What? Can you do that? Can you factor that? Sure you can. Okay? Just treat tangent as if it was a variable, like x or something like that. So how would you approach factoring that? Well, I don't know that you can factor it, but we hope we can. Now, unfortunately, the first term has several ways you can factor it. Okay? I sort of unfoil. What's one way to factor 4 tangent squared? Okay, 4 and 1. So you could say 4 tangent theta. Over here, do a tangent theta. And that certainly does multiply to be 4 tangent squared. Where do we look next? The sign of the last term. Now, what does that tell you? One of these is a plus and one's a minus. What order you want it? You choose. Minus and plus? Okay. Now what? What's the possible factorization of 3? 3 and 1. Is that how you want it? 3 and 1. Okay? Let's see if indeed you factored correctly. I think I was looking at the book, so you probably did. Okay? 4 tangent times tangent, sure enough, is 4 tangent squared. What I'm doing is foiling now. 4 tangent times tangent is 4 tangent squared theta. Then we do the outer, okay? And that would be plus 4 tangent x. And then we do the inner, minus 3 tangent, only it's theta, not x, okay? And then we finally do the last, and that's plus or minus 3. So 4 tangent squared theta, we know that's right. These add to be plus tangent theta. Sure enough, that's right. Minus 3. Ding, ding, ding. We got it right. And we're a happy face, aren't we? Because we got it right. Okay. Good deal. Okay. So you factored that correctly as well. Checkpoint here, 2 more that you can do. Let's move on to example 4. It says, on occasion, factoring or simplifying can best be done by first rewriting the expression in terms of just one trigonometric function or in terms of sine and cosine only. I really like that last technique, writing in terms of sine and cosine only. Unless there's something easier to do. I always go for the easy one, okay? But if there's nothing else to do, that's my next thing, is try to get it in sines and cosines only. So here we have example 4, factor this. Cosecant squared x minus cotangent x minus 3. Oh my. Problem here is you got 2 different trig functions. The previous one, at least everything was in terms of, what was it? Tangent. Yeah, they were all tangents. Now we got a cosecant cotangent. Hey, don't know what to do with that. Oh yeah, we do. What would we do? Okay, Pythagorean identity will relate. Okay, there is a Pythagorean identity that relates cosecant squared, but not to cotangent, to cotangent squared. If that was a cotangent squared, by all means go with Pythagorean identity. Okay? This is squared, that one's not. We don't have an identity that does that. Okay? Unless you have a radical in it somewhere, and we don't. So what we do, remember I said one of my favorites, if I can't think of anything else to do, I'm going to get it all in terms of sines and cosines. So, how do you get cosecant in terms of either sine or cosine? What is cosecant? What is cosecant? Get to know these things. They are important. You'll use them a whole lot. A little louder. What is cosecant in terms of sines or cosines? It's 1 over sine. So this, since it's squared, that's 1 over sine squared x. Minus, and what is cotangent in terms of sine and cosine? It's what? Get to know them. All right. Both of you finished? Thank you. All right.
Thank you.
And go on and grade it from here. Same with you. All right. Okay.
Thank you.
All righty. What? It's what? Sine over cosine? That's cotangent? Yes. Say again? Okay, but that's not in terms of sine and cosine.
Oh, cosine.
Cosine over sine. You had the pieces together, you just didn't put them together. This is an x, not a theta. Minus 3. Okay, we've still got some problems, folks, but at least we're maybe a little better off. Rather than two completely different trig functions, we have two that are different, but they're related. All right, what might we do next? Any ideas? What's messy about that? Yes, you have denominators there. I know Amber loves her fractions, but, you know, sometimes it's simpler to go without them. Okay? So what could we do? Find. If you're adding or subtracting fractional forms, you have to have common denominators. What would be your least common denominator in these three? Second?
Oh, the 3 of them?
Yeah. This one's over 1, by the way. Okay. No, it has to be. No, you got me to write the wrong thing down. Look at you. No, it has to be common to all of them.
So sine. How you make it relate if it's on that one is 1 and those that sine is 2 and that sine x?
Okay. What if this was a 6, that was a 2, and that's a 1? What would be your least common denominator?
2. 1.
Has to be common to all of them. 6 won't go into 2. 6 won't go into 1. But they'll all go into 6. So that's the common denominator. Okay? Okay, that was my third choice? Okay. Now, what would be your common denominator there? Sine squared, okay? So this would be 1 over sine squared x, because that was already there, minus, now I want to get that to be a sine squared, so I'm going to multiply the denominator by another sine. Right? So that becomes sine squared x. But if I multiply the denominator by sine, I've also got to multiply the numerator by sine, right? So that would be sine x cosine x, right? And then here in the last one, if I multiply by sine squared x, then I've got to multiply this by sine squared x. Okay. So now what we have, so this would be 3 sine squared x over sine squared x. All right. So I'm going to change the order somewhat and make this minus 3 sine squared x minus sine x cosine x, which I still don't like, plus 1, all over sine squared x. Okay. We still got problems, Houston. Okay. Sorry about that, folks. This will work, but I've done too much work for too little value. So let's back off. And actually, I think one of you may have said it. Okay? Did one of you say Pythagorean identity? I thought so. Okay? And the reason that works here is because the Pythagorean identity that relates cosecant is cotangent, right? So what is cosecant squared in Pythagorean identity? One plus cotangent squared x. I can't write. Goodness gracious. Okay. Okay. Not quite what we want, but pretty close. So let's write that. Instead of cosecant squared, we are at 1 plus cotangent squared x minus cotangent x minus 3. So what can we do with that? Combine like terms. And what like terms do you see? 1 and negative 3. What do those combine to be? Negative 2. So we have cotangent squared x minus cotangent x minus 2. Now we see if we can factor. I think we can now. What's the only possible factor of cotangent squared? Cotangent x times cotangent x. Okay, where do we look next? Sign of the last term is negative. That tells you these have to be different. 1 plus and 1 minus. And then what's the only possible factorization of 2? 1 and 2. In that order, 1 and 2. Let's see if that works. Cotangent times cotangent is cotangent squared. Got it. This will be minus cotangent x plus minus 2 cotangent x plus cotangent x. That would be minus 1 cotangent x. Got it. And this will be minus 2. Yes, we have it. So that's the simplification of that. Doesn't look all that simple, but it is a simplification using the Pythagorean identity. Okay? Let's clear those out of the way. Any questions on that? And let's do example 5. I don't think they did 5 either. So let's do example 5. Sine t plus cotangent t times cosine t is equal to sine t plus, oh wait, yeah. They're doing the problem for you, so I don't want them to do it. I want us to do it. All right. What are we going to do to simplify that? Here we have 3 different trig functions in there. Say again? Okay, what 2 are alike? A little louder. Okay, the cotangent is made up of the other two how? Cotangent is cosine over sine. So that's our first step. Okay? We'll write sine just like it is because it's already in terms of sine, plus, and this will be cosine t over sine t times cosine t. Okay, and we got to figure out what that is. Well, again, we have denominator in one term but not in the other. So what we need to do, least common denominator, which would be sine t. So we're going to put a sine t down here, but if you do that, you have to multiply by sine t up here, which makes it sine squared t. Well, now we've got sine squared t plus cosine t times cosine t is cosine squared t, and that's all over sine t. What's sine squared plus cosine squared? We know that, don't we? Sine squared plus cosine squared? 1 over sine t. But what's 1 over sine t? We know. That's cosecant t. Got it. So this thing really did simplify to something that was unlike anything else in the problem. Okay? Cosecant t. All right? One more of these that they didn't do. Any questions on that before I erase it? Everybody got it? Everybody got it? Okay, I guess so. Last one before we go back to the slides. This one, perform this addition. Sine theta over 1 plus cosine theta plus cosine theta over sine theta. Perform that addition. Now again, that's Amber's favorite form, fractional form. So how are we going to add those two fractional forms? How? Yes, and what would be your common denominator between those two? Hint, they have no common factors, so what do? Multiply them together, exactly. So what we're going to have to do is multiply the first one by sine theta, and if we do that, we have to also multiply the numerator by sine theta, right? The second one, we have to multiply by 1 plus cosine theta, and we're going to have to do that to the numerator as well, 1 plus cosine theta. All right. So your denominator becomes sine theta times 1 plus cosine theta. Okay? Your numerator becomes, we're going to add them together, you got a sine squared theta, right? Plus cosine theta plus what? Here you have a cosine theta times 1, that's cosine theta. And you have cosine theta times cosine theta, that's cosine squared theta, right? With me? Okay. Now, especially in that numerator, what two terms look like they go together really well? And what do those become? Yes, that becomes a 1. So this simply is a 1 plus cosine theta, right? That's all that's left in the numerator, right? And what's in the denominator? Sine theta times 1 plus cosine theta. See, I chose not to multiply those out, leave it factored. Guess what you get here? Those divide out, leaving you a 1 in the numerator. And what's 1 over sine theta? Say again? Cosecant theta again. Y'all like that one, don't you? You've had it twice in a row. Cosecant theta. All right. Every one of these has a checkpoint. Really suggest that you look into those. Okay. See, Amber left just so she could look into it sooner. Okay. Just kidding. What's that? Oh, no. You can't mean it.
It's 10:47.
All right. We'll start next time at example 7. And there is a slide for example 7. Okay, wait. Let me give you some homework exercises. Do any of the odds 7 through 13. Do any of the odds 15 through 19. In fact, I would do all of 15 to 20, but the answers in the back are only good for 15 to 19 odds. Do any of the odds 21 to 27. Do either 29 or 31 or both. And try 33. And any of the odds 35 to 43. We'll stop there and pick up the rest of those later. Okay.